Okay, so question 5. Figure 9 shows a tugboat moving at a constant speed. The weight of the tugboat is 24,000 newtons. The thrust force caused by the propeller is 15,000 newtons. So immediately I'm picking out a few things from this question. Firstly, this word constant speed. Constant speed tells us we have no acceleration. If we have no acceleration, we also have, therefore, no resultant force. That means the forces must be balanced vertically and horizontally. So, given what I've been told about the weight of the tugboat and the thrust force from the propeller, I can also make statements about the forces acting against the boat backwards and also up on the boat too. So 5.1, the question asks us, describe the other forces acting on the tugboat when it is moving at a constant speed. Well, I've just kind of started to go at what I'm thinking about here, so maybe I could just mark these forces on. The weight of the tugboat is 24,000 newtons. Now, our tugboat is not moving up or down. In fact, it is stationary, vertically speaking. Therefore, the force up on it must also be 24,000 newtons. It must be equal to the force down. Similarly, the tugboat is moving at a constant speed, presumably from left to right. We're told the thrust force from the propeller is 15,000 newtons, and the forces backwards, therefore, if this boat is travelling at a constant speed and not accelerating, there is no resultant force. Therefore, they must also be 15,000 newtons. Just to remind you that a resultant force is the single net force which acts as a result of the combination of all other forces. So horizontally, we have 15,000 newtons going forward, plus 15,000 newtons, and 15,000 newtons going backwards. 15,000 minus 15,000 is 0 newtons. So we have a resultant force of 0 newtons. Anyway, let's tackle this question. So, describe the other forces acting on the tugboat when it is moving at a constant speed. So, firstly, I'm going to talk about let's do the resistive forces acting backwards. So, if the boat is travelling at constant speed, the resultant force is 0. Full stop. Therefore, the forces, what I'm going to say is here, the resistive forces, i.e. the forces resisting the forward motion of the boat. And what will those forces be? Well, there'll be some air resistance, and there will also be some resistance from the water. You can write water resistance, I suppose, or drag you could call it. Therefore, the resistive forces are equal in size, but opposite in direction to the thrust. They're both 15,000 newtons, just in opposite directions. So that is the resistive forces. We've talked about that. Now, we were also told about the weight of the tugboat being 24,000 newtons. The final force we need to talk about is the one going up. So what supports a boat that's floating in water? Well, a boat floating in water is supported by upthrust. Again, this boat isn't accelerating up or down, it's floating. Therefore, that up thrust must balance the weight of the boat. They must be the same size. So we can say, since the boat is floating, there is no resultant force on it. It is not sinking, it is not rising. There is no resultant force on it. Again, a similar structure to last time. Therefore, the upwards force, and in this case our upwards force is called up thrust, must be equal to the weight of the boat. And we've established, or we've been told, that is 24,000 newtons. And implied in that, I've said the upwards force, implied in that is it's going in the other direction. Okay, so that's 5.1. Bless me. All right, I've kind of done this already, 5.2. The tugboat slows down as it approaches a ship. Key word here, slows down. This tugboat is decelerating. To slow down or decelerate, there must be a resultant force backwards. Draw and label a free body force diagram to show the forces acting on the tugboat as it slows down. So we're going to think vertically and horizontally again. Vertically, there's no change. We had a weight of 24,000 newtons, and the boat is still floating, so we're going to have an up thrust of 24,000 newtons still as well. Notice that I've drawn the arrows of the same size. What about horizontally now? Well, the key thing to recognise here is the tugboat is slowing down, it's decelerating. Therefore, we must have a resultant force in the backwards direction. So if this is my thrust going forward, my resultant force going backwards, my resistive forces, must be larger. I imagine they will allow you to have drag, water resistance or air resistance here rather than resistive forces. Let's take a look. So we're having a look at question 5.2. Here we go. So weight and up thrust arrows are drawn equal in size and opposite in direction. Resistive forces arrow is larger than the thrust arrow. Okay, so they've said resistive forces and they're accepting air resistance, friction or drag. Drag is a nice one to get away with, so it covers a lot of resistance forces. Good. You're also allowed the absence of the thrust arrow, so it's possible that they've turned off the engine altogether or released the clutch and the boat is just moving slowly or slowing down that way. Okay, 5.3. Oh, I can already see a parallelogram of forces here. So figure 10 shows two tugboats pulling a ship into the harbour. We've got our large ship here and our two tugs here and here. Each tugboat exerts a force of 100,000 newtons, so each of those is 100,000 newtons. But the angle between the force, we are told, is 40 degrees. Complete the vector diagram in figure 11 to determine the resultant force exerted by the two tugboats. This is going to be a geometric construction, and what you're going to be doing is completing the parallelogram. So I'm going to copy this line over here, and I'm going to copy this line over here. There are several ways of doing this. Perhaps you've been shown how to do it with a compass. You could also do it in terms of angles as well. If this angle in my parallelogram is 40 degrees, this angle over here is going to be 40 degrees. In a quadrilateral, like a parallelogram, we have 360 degrees. 40, add 40 is 80. 360 minus 80 is going to be 280 degrees. So the other two angles, here and here, add up to 280 degrees. It's 140 degrees each. And then I would also draw 5 centimetre lines too. So that would allow me to complete my parallelogram. If I was doing it, I would of course use a protractor and a ruler to complete this parallelogram. But you're not finished here. What is my resultant force? Well, my resultant force when I draw a parallelogram like this is the line from the origin, the start point, to where these two force arrows meet again. What will I do with that? Well, using the scale, if 1 centimetre is 20,000 newtons, I would measure this line, and shall we say this comes out as 8 centimetres. I'm not sure what it is off the top of my head. If that's 8 centimetres, then it's going to be 1 centimetre is 20,000 newtons, therefore 8 lots of 20,000 newtons is 160,000 newtons, like so. We can check, how close was I guessed the length of the line, so 192 to 196,000 newtons. That means that this line here was 9 point something, was it 1 centimetre, 192,000 to 196,000. Yeah, 9.6 or 9.8 centimetres that line would have been, if you were to draw it yourself. Okay, that was question 5.